Greetings, everyone. So this is going to be our first attempt at our online learning. And so we're going to start with a short video today and see how it goes, and then continue from there and make changes as we need to. So to start off our topic for today, I'm going to go back and do an example that we already know how to do, and then talk about how we're going to modify this with our new material for today. So here's our example. Let's find the integral from 1 to 2 of 1 over x squared dx. And so this is definitely something we know how to do. Here's what we would do. We would say this integral is equal to, and then we would do a quick rewrite of our function 1 over x squared. We would write it as x to the negative 2 because that puts it in a form where we can easily find the antiderivative. We just add 1 to the power, divide by the new power, and so we get x to the negative 1 over negative 1. And then, of course, we still need to remember to plug in our 2 and our 1 and subtract. Well, let's rewrite this x to the negative 1 over negative 1 to make it easier to plug in these numbers. Of course, the negative 1 just makes everything negative. And that x to the negative 1, to make the negative exponent positive, we just move it into the denominator. And so it would be an x to the positive 1 in the denominator. Of course, I don't need to write the positive 1. And since everything fell out of the numerator, we've just got a 1 left up there in the numerator. And we would still plug in our 2, plug in our 1, and subtract. And so let's go ahead and do that. We plug in the 2, we get negative 1/2. We subtract what we get when we plug in the 1. That's a negative 1 over 1. And so now we've just got a little bit of arithmetic to do. Of course, this just simplifies to negative 1/2 minus negative 1, which would be negative 1/2 plus 1, which is just positive 1/2. Okay, so that's the example that I want to start with, and of course we already knew how to do that. I also want to note what this represents. So this integral represents area A that we're going to indicate here. And if you look at this 1 over x squared function, you could use Desmos to graph it, but it looks something like this. Now, of course, we only care about the part going from x equals 1 to x equals 2. And so if I can find my red pen here, we'll shade that area. And of course, since that's above the x-axis, where this integral really does represent this area, A. Okay? If it were below the x-axis, the integral would represent the negative of that area, A. Okay, so that's our first example. What I'd like for you to do now is to do 2 more problems. I'd like for you to do this same problem, except make it the integral from 1 to 10, 1 over x squared dx. And then I'd like for you to do the same problem, except make it the integral 1 over 100, 1 over x squared dx, right? So all we're doing here is just changing the top number. Instead of a 2 in the first problem, it's a 10. And instead of a 10 in the second problem, it's 100. I'd like you to do both of those and draw the picture that goes along with them too, to see what they represent as far as the area goes. All right, so if you'll pause this video and do both of these problems, I will check back with you in a moment and see how they went. Okay, so hopefully you've tried both of these problems. And so the first one, you should have gotten a result of 9/10. And the second one, you should have gotten a result of 99 over 100. And this is actually pretty interesting, these two results, because this area that we're shading goes all the way out to the x value 10. This area that we're shading goes all the way out to the x value 100. All right, that's a long way horizontally, but you'll see our area is not getting that much bigger. That's of course because vertically, as we go out horizontally, that area is getting thinner and thinner. And so what we're going to talk about today is what happens if we go all the way out to infinity, right? We get this unbounded region that goes all the way out to infinity to the right there. And so this topic is called improper integrals. And they're called improper integrals because one of the numbers is going to be replaced by some kind of infinity symbol. So here's the definition that we'll use. The integral from a to infinity of a function, f of x dx, is, by definition, of course we don't have a definition for this, but by definition, this is going to be the limit as t approaches infinity of an integral from 1 to t of our function f of x dx. Okay. And so, of course, if we take this limit out of the picture and we replace t with any old number in the world we want, we know how to do this integral, right? This integral here. It's just our usual, like those first 3 examples we did, the one I did and the 2 you did, right? So we could replace t with 2 for that first example, or 10 for that second example, or 100 for that third example. And all this is saying is that now we're just going to look at all those results and take a limit as t goes to infinity. So let's jump in and do our first example of an improper integral. Find integral from 1 to infinity, 1 over x squared dx. That's going to be our task. Right? And of course, this is an improper integral because it's got an infinity as one of the limits of integration. So here's what we'll do. The very first step is going to be to use our definition to write this integral from 1 to infinity, 1 over x squared dx is equal to the limit as t approaches infinity of the integral 1 to t 1 over x squared dx. And then we're going to write another equal sign for our next step, but we're going to do some side work instead of cluttering everything up in this main piece of work here. And so our side work is we're just going to look at the integral part of this expression and leave the limit out for the moment. Right, so we'll look at the integral 1 to t 1 over x squared dx. And here we're just thinking of t as just some random number, just like with any old integral. All right? And so what we'll do here is just the way we did the previous example. We'll rewrite that 1 over x squared as x to the negative 2 so that we can take its antiderivative. We know the antiderivative just like in the previous example. X to the negative 1 over negative 1, plug in t, plug in 1 and subtract. And again, we want to rewrite this antiderivative x to the negative 1 over negative 1 as negative 1 over x. Still remembering we need to plug in the t, plug in the 1 and subtract. And let's do that now. So we get negative 1 over t minus negative 1 over 1. And of course, that's the same as negative 1 over t plus 1. And if we think of that, we can combine those, well, actually, let's not even do that. Let's just negative 1 over t. So this integral comes out to negative 1 over t plus 1. So now, with that side work, we can return to our original calculation where we used the definition of this definite integral. And we can say, all right, now that was the limit as t goes to infinity of this integral 1 to t. And we could say now that's the limit as t goes to infinity. We just said that integral came out to equal negative 1 over t plus 1. Right? So we're replacing this integral with what we just did with our side work. That integral is equal to negative 1 over t plus 1. And now we have to take this limit. And so this limit is actually a very easy one to take. Limit as t goes to infinity, negative 1 over t plus 1 is, of course, what happens as t goes to infinity. Well, this negative 1 over t, as t gets really big, that's like negative 1 over 100, negative 1 over 1,000, negative 1 over 1,000,000. It's getting closer and closer to 0. So in the limit, that quantity is 0. And so what we get in the limit is a 0 plus 1. Of course, nothing's happening to 1 as we're taking this limit. And so our final answer here is 1. All right, so that's our example that I wanted to go through here. And this is a super fascinating result because let's think about what this means. So I'm going to erase all this and draw a picture. And so here's our interpretation. So we just calculated that this integral, this improper integral, came out to 1. The interpretation is that if we look at this 1 over x squared, of course we don't really care about the part of it that's over here. But the part that's over here represents the area from x equals 1 to infinity. And so let's shade this region. And of course that shading just continues on forever and ever and ever to the right there. Okay? So this is an unbounded region. It continues on forever to the right. But what this example tells us is that the area of this region that never ends is a finite area, right? It's sort of an infinite region, an unbounded region that has a finite area. And so our interpretation is that the area of the unbounded region indicated, well, let's just say the unbounded shaded region is 1. Okay? And that's kind of one of these great calculus 2 results, just mind-blowing, that you can have an unbounded region that has a finite area. Okay? And so what I'm going to do is give you some practice problems to do that are just like this one. You use that definition of an improper integral, and let you kind of see what happens, and then we'll come back tomorrow and check in and see how you've done, and we'll do another short video. All right, so have fun with this, thinking about these areas of these unbounded regions.